Boy, oh boy, we are learning about mappings today, folks. I am so exhausted. I've been doing two 45-minute workouts a day, trying to do that, trying to stick to it. It's been a challenge. I'm not very far into doing it, but I'm far enough into doing it where it's a fun challenge, you know. But okay, so today we are going to learn about mappings in Solidity. So Solidity mappings, I just watched the video for it. There's kind of the lower level version of it where we can kind of show the assembly code for it, where we're stashing a connection between a variable and a value. Basically, it's a key value store. Is how I think of it. So mapping altogether. Let's look at a JSON object, right? JSON object. These are key values, right? When we look in JSON objects. So if you say this is the name of something, you can append it to the value of John. If you have the age, this is to the John's age of 30, and maybe it's a car. So and this object as a whole could represent like a man or something, right? Like const man equals name John with this age 30, car null. And then for mine, it would be name Ryan, age 28, and car Ford truck. So that's my understanding of mapping, is we're creating one of these, the key with the value. So let's dive into it. Let's kind of get more granular, more the blockchain terms of it. But just bird's eye view, that's what we want to keep in mind of what we're fundamentally building is a key with a value. Okay, so mappings. Mappings are an important data type in Solidity. With a mapping, we can take values of one data type and map them to values of another data type. Let's consider an example. Say you wanted to track balances of a bunch of addresses. So we're just going to look at the tail end of these addresses. We have B6, D4, and D3 of balance 500, 120. Based on what we've learned so far, you might think of creating an array of structs, something like this, where we're doing an address with a balance, and these would be our accounts. It certainly works, is what they say. When we need to find an address balance, we can iterate through the accounts to find the address we're looking for and retrieve the balance. However, there's a better way. There's always a better way. Shout out to Babson. We can use a mapping address to uint balances. Okay, so it looks like here we're assigning an address to the balance. We're like keeping those keys together. So the struct originally, we would take these two things and we would put them into a third thing, an account. But a mapping is saying, no, just take that thing and this thing and put them, associate them together. That's the mapping. So with a mapping, each address is mapped to a unique place in memory where it stores the uint balance. Looking up the balance is as simple as providing the address. Sorry, guys, my nose itches. It's as simple as providing the address to the mapping. Balance is address. Okay, so under the hood, the storage location is found by hashing the balances variable location with the address passed in. It's a simple lookup, much more efficient than iterating through an array of accounts or something. We can just look for the one address. Generally, it's better to try to use a mapping first and only use an array when you realize you need to iterate. It's probably more expensive to iterate as well. Now that we see how mappings fit into the picture, let's learn how to build them. Fun. Should be a good time, right? Right? Okay, so before we dive in, let's just preemptively understand kind of what we just read. So we're storing an address to some value in that example. So we're storing something to associate it to something. So I understand in memory what's going on is we store this thing with a pointer to another thing, right? So this mapping of an address gets stored in some location in memory, and that memory says, okay, if you ever look this thing up, it's also pointed to this thing, just FYI. Okay, so that's my understanding of what we just read. Mappings allow you to store and retrieve elements quickly with a key. The key points to a location in memory where the value is stored. The key can be any basic data type in Solidity. Cool. It cannot be a reference data type like in a struct or a array. The value, on the other hand, can be any Solidity type. It can be a struct, an array, or even another mapping. Okay, so the value of a mapping can point to another mapping. Even we can have one value stored pointing at another value, which points at another value. That's kind of fun. Okay, so let's see an example of a mapping. We can map an address to a uint, and this would associate the address. Guys, my ear itches too. So I just went on a run. I was like walking through the forest. You know, there's like a little hiking trail thing, and I think I've got like little like I don't know if they're like little mites or something, or like bugs. Not like, you know, crazy ones, but just I felt like one on my, like an ant or something on my leg. You know, nothing like crazy. I didn't mean to say mites. Mites sounds nasty, sounds dirty, but you know, like a little bug or something's on me. So that's what I'm like constantly scratching and itching and stuff. Either that or a poison ivy or something. Who knows? But anyway, so we're here for mappings and not trails and hiking. Okay, so here's an example of us mapping an address to a uint score. So again, this address would always point to the score variable. Okay. So this is, let's see. We're using the message sender as the key to look up the score in storage. Got it. So we can look up the score just by saying, hey, the message sender, here's the address. I'm the message sender, wallet number 1, and I'm trying to find the address with the number 1 with the score with it. So that's one way to do it. Okay. The variable score takes an address and maps it to a uint. Each address will be mapped to its own unique uint value that it can retrieve and modify. The add point function uses the message sender as the key to update the location in memory. Okay, that's cool. So it adds the point of, wait, why are we doing that though? Does it need to do that, or does we can also update that location in storage? Are they just showing a point here? Because I thought that's what the mapping did alone was points here. So we can also update the location in storage. Let's reread that one more time because I'm not fully understanding the point of it. So the add point function uses the message sender key uses the message sender as the key to update a location in memory. This location in memory for a value is initialized at 0. We can add to it by using the message sender key as shown above. So the score mapping is public, which means that there will be a getter function created automatically, I like to say. We can make a request to an Ethereum node invoking this getter function with an address and get a uint back. Let me move my face. Our goal: create a public mapping called members, which maps an address to a bool. Okay, so we could start with a mapping, and we want to say address to a bool, and it was called public members. Boom, not members, but members. This bool will indicate whether or not the address is currently a member. So we'll just store a true false value, create a external function called this. Got it. So that's what it was doing up here. It was just assigning that value, I suppose. Okay, so add member, let's see, external, and okay, so create an external function called add member, which takes an address. So let's go ahead and do this. Address, we'll say underscore address for now, not addresses, but address, and adds it as a member. You can do this by storing true and the data location corresponding to the address in the members mapping. Okay, so how can we do this? If we do members at this data location, and do we just assign it to true? Is that what I'm roughly garnering here? So this was updating the score is what it was doing. Got it. So adding points. Okay. Sorry guys, I had a misunderstanding of what the function add point was. I thought for some reason it was saying add pointer as like add an additional pointer, and I don't know why I thought when I thought wallet 1. Thought indexing to wallet 2, we could look up wallet 1 by looking up wallet 2. Complete misunderstanding. So what they're doing is adding a point to the score variable, the value score. What we're doing is adding a true to the value bool within the members instance. Okay, so I think all is well, potentially. Let's see. And potentially not. I don't know if we need to do anything more. Let's see. So I believe that's okay. So we store this Boolean value every time we call this function. So if I'm wallet 1, I pass in wallet 1 into this add member functionality, and this gets stored on the memory here. But what are we storing? What is it pointing at? Right? Is that the correct understanding? So we have the address is pointing at something, and this is what we're now mutating here is a Boolean value, a Boolean expression, and we've stored the value true. But so now when I look up wallet 1, I could say, okay, it's pointing at true. They are a member. Okay, I think that's a full circle understanding, right? Full circle here. Full circle. Okay, so mapping retrieval. Compared to arrays, retrieving a value from a mapping is quite simple. Okay, arrays, we got to find, we got to do a whole bunch of stuff, but doing a mapping through students is as simple as this: return fun. Okay, so we just literally pass in the address associated to the map, this little square bracket deal. That's fun. Okay, so versus this where we have to iterate through it all, return the one that matches this one. We just directly get the one that's looked up by this one. Okay, that is cool. So it's almost indexing in a sense, right? We can just go directly to it. Boom, there it is. Okay, so to find if the student address is in the array, we have to iterate over the array. For the mapping, we can simply plug in the address. Choosing the right data structure is half the battle. It can keep the code clean and use up less gas. Curious? That is actually, let's understand that real quick. That's actually a super important point, especially with smart contract development. We want to optimize for as little as gas as possible. So choosing the right data is half the battle. We want to always opt for the least amount of gas, especially with these smart contracts. That's huge. Okay, so curious how the value lookup for the mapping works under the hood. Let's take a look into the details. Always love to see how things work. We have the cache 256 from the SHA-3 family. We love it. So storing the value inside of a mapping has two things: the variable position inside the contract and the mapping key to find the value. Love it. So the variable position is determined by where the contract where the variable in the contract is defined, or the mapping is defined. So in this example, balances would be in the storage slot 0 because it's the first variable. If there's a uint declared above it, so if we just had one little variable right here, so right now members is in the 0th position, so uint public, we could say variable right here, right? Some variable dot. So now the mapping would be in index 1. The mapping key will be the address for the balance we're trying to find. We can take the variable position and the mapping key and hash them together. Okay, so is this the mapping key, the storage slot, or the variable position is right here? Okay, the mapping key will be the address. Got it. Okay, so right here, this is our mapping key, storage slot number 1. This will result in a hash we can look at. Okay, so that is cool. That is really cool. We can use to find the value stored by the mapping key. If we need it, we could also use the sload method in assembly to do a direct storage at its location to find how this works under the hood. Look at the details. Boom. So your goal is member. Create an external function called isMember, which takes an address. Okay, let's do this. So function isMember takes an address. Say address. Believe it's external is what they said, right? External. Boom. Here we go. And it returns a bool. So let's say returns a Boolean value here, indicating whether a member is an address, a person is a member or not. So what we can do is actually, I believe, just return this value because it should declare true and false. So we'll be return true or false if they're a member. So we don't have to check, for instance, if this is true. Should, by virtue of this, just return true. Okay, cool. So that's worked here. Let's go to the next one. So remove member. So mapping removal. For arrays, removing elements can be an expensive operation, especially if you don't want to leave any gaps. Let's say you had an array containing the unsigned integer values 1, 2, 3. Removing the first element 1 would mean you have to shift the values 2 and 3. So if we took out 1, we'd have to go boom and boom. Move 2 over to the 0th position and 3 over to the first position. For a bigger array, this could be very expensive. In this case, you could use a linked list where you could stitch the previous node to the next node instead of having to shift the elements. Okay, very interesting. So removal is quite simple. For example, in this students mapping, we can go over here and we can just say function remove student at this address is now assigned to false. Simple code. So we provide the address to find the memory location and set it to false. Okay, so this is just kind of a cheeky way of doing it, I suppose. But if we were mapping to a uint value, how would you do that? Would you assign it to a zero value, or would you assign it to null? Or would you consider using the linked list at that point? Questions I have. So create an external function called remove member that takes in an address. Let's do that. And it's going to return a bool, or actually won't return any bool. It'll just be external. And what we need to do is just assign this to false. So I'm questioning if this only works because we're assigning the true or false value just as true and false, right? That's how we're kind of keeping track of if someone's a member or not. But again, like I said, if we were using a mapping for another question, well, this needs to be named different. But if we were using a mapping for something else, another value store, I don't know if this approach would work, or would it? I think it depends. Okay, so mapping with structs. Here's what the mappings, or here's where the mappings get interesting. We can map to different types. Let's start with structs. We have contract, boom, 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 struct, collectible, address, boom, boom, boom. Nice, nice, nice. And we can map a UINT to a collectible. Okay. So how does that work when we store? Let's look at this. I'm going to zoom this out a bit just to organize the code a smidge. So we have this UINT being mapped to this struct here. And how does that work? So this ID is what the UINT is, and that's indicating the collectible associated with it. Okay, so let's say ID1 has a collectible with address OX123, Boolean for sales true, and the price is 1 Ethereum or something like that. Okay, so find the collectible by the ID passed in. That's why you do that, because you can find a collection of data with one ID without having to iterate through. Okay, so that kind of makes sense. Guys, I'm just narrating my brain talk out loud. I think this is brilliant. This is brilliant. Okay, so purchase the collectible. Now we can also do other things with it or not. Collectible.owner is the message.setter. We set it to false if someone's purchasing it. So first, the very first thing you do is look it up by the storage. Okay. And then I believe we use the storage keyword because we're actually changing the value here. If we were just looking it up, we might be able to get away with the memory keyword. Okay, so we are able to look up the collectible using the UINT ID passed to purchase. Then when we have access to the struct, we could sell it to its new owner. Your goal, user mapping tokens. Got it. Okay, so we want to create a public mapping. So mapping users that will map to an address. Oh, that will map a address, forgive me, to a user struct. And this is going to be public, and we'll call it users. And then we also need to build the struct user. I suppose the struct could exist above the mapping for code organization, but I don't know if it matters necessarily. Oh, we already have the struct up here. Didn't even realize. Okay, great. Okay, so create an external function called create user. And we'll say function, boom, create user, external. And what does it do? So this function should create a new user associated to the msg.sender and the addresses deal. So we're going to do some stuff very similar to what they've done up top here. So we want to say user storage, and we're using that storage again because it's a, what is it? We're actually building a data structure here, and it needs to be, it's state mutated within the contract, not just memory, not just call data. And we want to assign this to the message.sender. Boom. So I think that's proper user storage. Just wonder why my storage isn't highlighting blue, right? Okay. And what else do we want to do? Address in the user's mapping. So how do we store it? This function should create a user and associate it to the message sender. So let's think about it. So the address is associated to the user. Is this kind of what we want to do? Let's think. So the other one we mapped addresses to a message. So yes, this would be the address, and then we want the user, right? Something like that. It's fundamentally what we want, right? We'll run with it. Okay, so that's, I believe what it needs to be. And the balance of this user, so user.balance should be set to 100, and user.isActive should be set to true. Is active true. And let's see if this is roughly. Ensure that the create user function is called with an address that is not associated with an active user. So we need to require something here. Require. This is called with something that is not an active user. So that user is not active already. Return user, and we need to pop this here. Okay, let's try. Nope, no good. So implicitly convertible to UINT 256. UINT balance. Do we need to pass in an address from the function? Should create a new sender, boom, boom, boom. The address. Okay, let's take a peek, see what they did. Require user's message.sender is not active. User's message. Oh, they did it way cleaner, way simpler. Okay, so users. Let's see, users equals set user, assign it to 100, right? True. Do I need to do the new keyword? I forgot. And then what was this bit? This was require the users above. So require users, pass in the MSG sender the address of the person calling this, and then that is active is equal to false. believe, right? Users equals new user. Now, what was this bit? What was this bit? Okay, let's take a little peek-see again. Users message sender. Okay, I say they stored with the thing. That's what it was. That's what it was. So they stored with the actual address. Got it. Okay, beautiful, beautiful. Okay, so I didn't really get that, but at least the first go around. So let's just quickly crank through it one more time. So create user here. It's an external function. Because I like to do this quick repetitions, right? Right away. So, okay, require, we want to make sure that the user is not already here. So we'll look up the user by the address. Needs to equal, the dot is active, needs to be equal to false. And then the user's message.sender, we're going to assign this new value in storage to set this user's balance to 100, and then that they are in fact active. Sweet. Okay, we got it. We got her down. Got her down, folks. Okay, structs map to. Let's get cruising. Types of balances. Broadly speaking, smart contracts deal with two types of value transfers in native currency Ether, which is stored and transferred using the native EVM mechanisms, the value in the message call and the balance on the address. A storage value, which can represent any type of value on change and updated by modifying storage variables. Okay, so we can either do it through Ether or by updating some sort of UNT or some sort of value on chain, I suppose. Okay, so in the smart contract you are building, you are maintaining your own balances in the user struct, which has no relation to Ether. This means that to transfer balances from one user to another, you could just update the struct value. So our goal is to create a external function called transfer. And I imagine, say, users at this address, right? Takes two parameters. So we have an address, and we'll do an underscore here, underscore address. So create an external function that takes two parameters, a address and then an amount. I forgot that bit. So a uint of an amount. Sweet. And we'll say uint balance, boom, equals amount, I imagine. And then maybe this would be, I haven't looked at the instructions quite yet, but I imagine maybe something like this, where we remove the balance from the other guy. Okay, so in this function, the transfer amount from the, what does it say? So add a uint for the amount. In this function, transfer the amount specified from the balance of the MSG sender to the balance of the recipient address. So maybe we don't need to do this, but maybe that would actually work. I think what they've requested is set these things to assigned. So assign this one to this one, like this, I believe. But I'm going to try the negative deal first. Let's see. Ensure that both addresses for the transfer function have keys. Okay, so we've done some sort of deal here. Boom. Let's see. Call did not revert, or call did not revert as expected. So what do we got to do here? So ensure both addresses used in the transfer function are active. We do need to do that. So let's steal this require statement, and we'll say is active equals true, and we'll do that for both of them. Let's try that one, right? Where was it? Why was it not working? There we go. Okay, so that's one bit we need to do. If either of these conditions aren't satisfied, revert the call. I thought require statements do just revert the call. Ensure the MSG sender has enough balance. Okay, that's what we need to do. So that the balance of the sender is greater than the amount, greater than or equal to the amount. Really, it should be greater. Technically, we got to account for gas fees, so amount plus gas fees, but tomato. Okay, so that was not it. Boom. What about that? What about that, huh? And then let's do the way that I read it initially, or how they want it, I believe. Let's see. Now, what does it say? Error, expect a transfer to increase recipient's balance. Is this the recipient? Do we have these backwards? Should this one be the recipient and then this one be the sender? Will we run it one more time? I'll take a peek, see if that's not it. Okay, let's see. Let's see what they did. Okay, so we need to require a whole bunch of stuff, or require users to message on sender is active. Okay, we got that. Require users to is active. Okay, users message that sender balance is above the amount. Oh, I see. I assigned it to the amount. I needed to add it to the amount. Got it. Okay. I think we were almost there. Almost there with it. Great. Okay. Guys, I think this is the last bit. Nested mappings. As shown in the previous stage, we could provide more complex types in our mapping values. Last stage, we showed it with structs. Let's try it with other nested mapping. Okay. So in this scenario, each vote ID points to a mapping address. So boom, we have a ID that's getting passed in vote number 1, which is mapping to an address, which is then mapping to a true or false. That's kind of cool. So it's mapping addresses to a bool, and that value is getting stored elsewhere. So first the address gets mapped to if they voted or not, and then we store those two pointed from some ID. Okay, so this allows each address to register a different vote with each vote ID. As a voter, we might call a function with an ID to register our choice. So function register vote. Okay, so we pass in that ID first, and then whether it's a true or false choice. And then it looks like the vote to address choice is assigned with the ID and then the address additionally. And then we finally take that. Okay, that makes sense. That makes sense if you think about it from first we have an ID one of like first vote in this voting box, which points to OX123, which points to the true or false if they voted or something like that. Or Republican Party or Democrat Party or something like that. Okay, so that's cool. Let's say there are 3 votes. IDs 212, 72, and 409. We can make the following calls from external from the contract. Voting contract register to vote. So what is this? Is this the wallet ID or this is the voting ID? Register vote for true vote ID. Okay, this is the vote ID, and this would register true without having to know the wallet ID. Huh. I don't know. Sounds like someone's trying to shimmy Sam some votes now that I think about it. Now that I think about it, I don't know. That seems like too easy to shimmy Sam some votes. Okay, so this would register true for the IDs 212 and 409 at our addresses. For 72, it would appear false. Okay, so these two true, boom, 72 false. Of course, the default value for a bool is false, so the second vote may be pointless unless we were to add it in another way, provided, wait, hold on. So the second value, they're just saying just for Booleans, the default value is false. But let's say the vote wasn't just true or false. Let's say it was like a specific party or specific candidate. You'd pass it in as a string here or something like that. Okay, so our goal, create a public mapping called connections, which maps, okay, this is going to be kind of a good one. So let's say mapping, let's get connections here. It's going to be public. And what is this going to map to? This is going to map to a map, which will map to a address pointing at a connection types, which is going to be this guy right here. Boom, sweet. Okay, so I think we've done that correctly. Let's just double check the syntax. Yep, looks like we're there. Okay, so that's an enum value, perfectly done. So unacquainted, friendly, family. Those are the connections types. Stranger, friend, or family. In connection with function, create a connection from the MSG sender to the other's address. Interesting. Okay, let's try to do this as much as possible. Let's see. So we want to get the connections, map it to the address first, right? So connections. Then we want the address or the MSG sender, and then finally, what's the last bit? It needs to be to the other. And this needs to be assigned to the connection type. I think that's right? So first it goes to our connections store of like, here's all of our data types. Get the address to, what is the other again? The second address. And then that's pointing at, I see. And that's pointing at whether they're a friend, a family, relationship, or stranger or something. Okay, so I believe that's correct. So we do the connections. What was this? Mapping, expected element of a different key type. Oh, so this wasn't right. I needed to go address. That's what I'm missing. Boom. Here we go, right? So it's an address pointing to, perfect. There it is. Okay, so that wraps it up. Let's talk about that last one a bit for a second, because I think that's going to be very, 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 very valuable to understand. I wanted Lucid Chart because I just like cleaned out my computer, so all my links are like broken. They're not working the same. Okay, so let's sign in real quick. I'll sign in with one of these guys, and let's see what we got. But basically in memory we stored that. That makes sense. And in my brain, it's clicking a bunch now of the bracket syntax, like the nested brackets. Not sure why that took so long to click in my life, but this always would intimidate me. But now it's not as scary because my brain is visualizing. I'll try to explain on the Lucid Chart because I think it makes a lot of sense now. Okay, so we have our connections, right? So this is going to be connections. Oops. We'll go. Whichever. Just close. Come on. Just come on. We're trying to develop here. We're not. Come on now. Okay, boom, we're here. So we have our connections, or in this case, lowercase connections, and these connections are actually pointing to a bunch of addresses But let's just take the example of one address, right? So it's pointing to an address, which is pointing to another address in memory. This is all in memory, right? Right. So this is also pointing to another address, which is pointing to a connection type. So let's say your address 0x123, and I'm address 0x124. So I'm saying let's connect 0x123. You're awesome. Let's be friends. And I'm sending you basically this request in memory is what I'm understanding. Friend, boom, okay. And this is all our memory is doing all the time on a lower level. So our connections holds all the pathways for all this stuff. This address points to my address points to you and the friend request I sent you, right? So that's what I'm understanding. And I see it now by this of like, okay, so first I go to the connections, then I take my address and I'm sending you a friend request. And that's the type of request it is a friend request. That's the fourth bit there. So there's kind of four things of data here that we're looking at. That matches here. So we have our connections, which is all of this. So it's a whole shebang here. But my address, right? So this one-way data flow, the connections is all of this stuff, right? Boom, 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 boom. And then my address is pointing at your address, which is pointing at the connection type I sent you. I hope that makes sense because in my brain, that's like a light bulb moment. Don't know why. Maybe you guys understood that really easily. I did not until now. This makes like a lot more sense. Seeing this, I'm much less intimidated by seeing these 2D matrices, if you will, or these brackets that are squared side by side with each other. I used to think of like, oh, it's like finding a variable within a list within another J index, right? So like when you did 2 for loops, you had an index for loop and then a J index for loop. For some reason, it's just like, oh, I'm going brute force with the first item and then going through the second one, da da da. But now when I see it like this, it makes a lot more sense. I'm just pointing from this bit to this bit to this bit to this bit. Duh. See you on the next one.